This is lecture 4G2 for Calculus 1, the rain gutter problem. This rain gutter problem is a classic problem both in trig and in calculus. You might have solved it in trig as well. Here in calculus, it's an optimization problem. And the goal is to optimize the cross-sectional area of the rain gutter so that it can carry the maximum amount of rain. To form the gutter, we start with a 30-inch wide piece of metal and bend it in thirds. So here's a sketch. So you see here that each side is 10 centimeters and the base is 10 centimeters. So there was your 30 centimeter piece of metal. And when you bent up the sides, you bent them both up at some angle theta, right? Now there's one thing that's not marked on here, and that is the height. Alright, that's the height. I'll mark with an H. We need to calculate the area of this rain gutter. Okay, so the rain gutter really has three sections. It has a center section that's rectangular and has a width of 10 and a height of H. Then it has two triangular pieces. And they have height H and their base is B, so I need to mark that up here too. So here's the base B. Okay, so I can just write this area as a sum of those sections. So 10H is the area of the rectangular section, this part right in here. Okay, and you have two triangular sections, and the height of those, or the area of those, is 1/2 BH. I have too many variables. I want to reduce this to a problem involving the theta, only the theta. So I have to do that on the next slide. So if I look at the angle theta, which is right here, I can figure out that the sine of theta is h over 10. Remember, 10 is a hypotenuse. And the cosine of theta is b over 10. Right? Because, you have opposite angles there. So h is 10 times sine theta, b is 10 times the cosine of theta. So here was my expression for the area. It had 10h, that was the base, that was a rectangle. I can replace h by 10 times the sine of theta and get this first term right here. Okay, now I have 2 times 1/2 bh, so I just have to take b and multiply by h. So b times h would be 100 sine theta cosine theta, and here's the sine theta cosine theta part. I'm restricting the angle to lie between 0 and pi over 2. Obviously, at pi over 2, you've got just a rectangular section. If you go beyond pi over 2, that area would be less. You don't have to make that restriction, but so here was that expression from the other page, and the goal is to find the critical point. So to find the critical point, I take the derivative and find a place where either the derivative doesn't exist or where the derivative is 0. But then I also have to look at the endpoints to find the maximum and minimum, or minimum. Hopefully we'll find the maximum. Taking the derivative requires the product rule, and then after that you have to use trig identities and do some factoring. So it's some work. Okay, say I want to take the derivative of the area with respect to theta. That's because I want to find the maximum angle, so I want to know how it varies with theta. So the 100 just sits out here, and I have to take the derivative of sine theta. That's easy enough, it's cosine theta. Then I have to take the derivative of the product, sine theta times cosine theta. That's where I have to use a product rule. So I'll hold cosine constant and take the derivative of sine. Then I'll hold sine constant and take the derivative of cosine, and this is what I get. Cosine times cosine, sine times the negative sine. That gives me 100 times the cosine of theta plus the cosine squared theta minus the sine squared theta. Now we have to, anytime we see sine squareds and cosine squareds, we think of the trig identity, the only one you really have to memorize, and that is sine squared theta plus cosine squared theta equals 1. So the sine squared theta on the end I'll write as 1 minus cosine squared theta, so I have everything in terms of cosine. So here we go. d theta is 100 times, I've got the cosine of theta plus cosine squared theta plus another cosine squared theta minus 1, or 2 cosine squared theta plus cosine theta minus 1. That can be factored. Now we like that because we want to set this to 0, so we only want factors. We don't want things we're adding in. That's too hard to find how those go to 0. Instead, we just want factors. So I have 100 here. That's not important. 2 times the cosine theta minus 1 multiplying cosine theta plus 1 would equal, if I FOIL this out, I'll get 2 cosine squared theta. That's the first term right here. Then multiplying the cross terms, I would have 2 cosine theta minus cosine theta. That will give me the positive cosine theta right here. Minus 1 times plus 1 gives me the minus 1. All right, so you should believe that. Now we want to find values of theta at which this is 0. So here's the derivative again. I want it to go to 0. I want to find the values of the angle that are 0. And I've constrained theta to lie between 0 and pi over 2. Okay. Obviously, when theta is pi over 3, then the second term here is 0. So at this point, the first derivative is 0. It is a critical point. There is no point where the derivative doesn't exist, so I just look for where all I care about right now is that the first derivative is 0. There are two endpoints. One is theta equals 0 and theta equals pi over 2, so I have to consider them as well. So to do this, I'm going to evaluate the area at all three angles and see which one is where it's the maximum. If theta is 0, the metal is flat, and the cross-sectional area is 0, and the rain will just run off wherever, just run off the roof. It won't have any meaning to it at all. It won't be a gutter at all. If theta is pi over 2, that's when the sides are bent up at right angles, so all you have is a rectangular section. The cross-sectional area would be 100. But at pi over 3, if you work out the area, you find that it is about 130, which is bigger. So pi over 3 wins. The maximum area is obtained when the sides are bent at an angle of pi over 3. And I'll show you that on the graph in the next page. So here's a cross-sectional area of the gutter. Here's a curve for it. Actually, it's a nice smooth curve. The maximum when the angle is pi over 3. Of course, this assumes that the length of the side, that you've bent the metal in thirds. And it doesn't matter that it was 10. You could have had any size gutter. This is still going to be the maximum, independent of the dimensions. But you have to bend it in thirds so that the sides, the length of the sides and the base of that rectangle are all the same. The analysis depended upon that.